Right, in this video we're going to talk about some of the other equations that might come up as a result of fields. So one of them is escape velocity, and the other is orbital velocity, and we'll probably talk about orbital energy as well. So orbital energy, those are the three things we're going to talk about in this video. So we'll start off with escape velocity. Escape velocity, now it's a very simple idea, is the fact that you've got a planet, and in order to escape from it, to escape outside of its gravitational influence, you've got to have enough velocity, v, in order to escape that field. And that is a fixed quantity for any object, dependent on the gravitational pull that's there. So we need to factor in gravity when we derive an equation for this value right here. So let's think about what escape velocity means. Well, if it's going to escape the gravitational field, then it's got to be able to get to infinity. So it's got to be able to get to infinity. And at infinity, well, we've come across this idea before when we've looked at potential. So if we think about potential energy as being at infinity as being 0 joules, because at that point it will be 0 because it's not in the field anymore. And then at this point here on the surface of the Earth, it's going to have a maximum negative value. So the idea is that if I've got to escape from this planet to infinity, and it's got to be able to permanently escape, I've got to have this velocity. And we've got to be able to put in the amount of energy to get it from this max negative value on the surface of the Earth to infinity, the value of 0. So whatever this max value is, that's the amount of work done you'd need to put in to move it from that point to infinity. Okay, that's the work done to move it from that point to infinity. But we're not talking about work done here, we're talking about a velocity. So let's start deriving and let's think about the kinds of equations that we might put in here. Well, in order for it to get up to this value here, we've got to have a value that's equal to the max GPE or potential energy here. So the equation for that is GMM over R. Again, if you don't remember where that equation has come from, go back, watch one of the earlier videos, it will explain where that comes from. So we've got this equation. Oh, bear in mind this is negative as well, because obviously in gravitational fields this is 0, and then everything is negative because we've got to put work in to make it less negative in this case. Well, in order to give that amount of energy, well, how are we going to get that amount of energy in? Well, we've got to put kinetic energy in, the same kind of way as if you've got a ball and you want to throw it to a certain height. You've got to have a certain amount of kinetic energy to get it to that height, and hence an amount of GPE, because the change in KE is equal to the change in GPE. There's a nice simple GCSE concept there. So with that in mind, we know that if I want to change the GPE, if I want to change this from whatever its max value is to 0, then I've got to have the same amount of kinetic energy in the first place instance. So at this point here, I've got to put in kinetic energy that's equal to this max value of the GPE to get it to go to infinity, because our change in KE is going to be equal to our change in GPE. So what's the equation for kinetic energy? Hopefully you remember, half mv squared, and we can actually set that as equal to GMM over R, because those have to be equate to each other in terms of a value. So in this way you can, for the most part, ignore the negative sign because you're just equating their magnitude to each other. So we want to set the V as the subject, so hopefully you can see we can cancel these m's. Bear in mind, obviously one of these m's is the m of the planet, that's Earth that we're on, and the m is the mass of the object that you're trying to move to infinity. So in this instance, what we've got here is we've got v, so half v squared is equal to gm over r. And so we can then rearrange this to v is equal to square root gm over r times by 2. Because of the half there. So that is actually the escape velocity equation, and this defines the velocity that's required, okay, the velocity that's required of a mass of the planet. Now this radius is a little bit confusing. This is the radius of the planet that it's trying to escape from. So in the case that's what this here, this is r here. Bear in mind, because r is always this value, it's not the distance you want to get it to, because the distance you want to get it to is infinity. So the escape velocity is based on the fact that you're trying to take it to infinity. So r is the radius of the planet that it's on. And obviously g, you know, is the gravitational constant. And when you work that out, you get an escape velocity. And this velocity is constant for all objects on this planet that want to escape this gravitational pull. Okay, so that's escape velocity. Let's have a look at another kind of similar derivation, although it looks similar, it's very much a very much a derivation with a different outcome. So when we're looking at orbital velocity, we're thinking about something that's orbiting around, say, our planet, so like a satellite or something like that. This is my poor attempt at a satellite. And that satellite is moving around in an orbit around Earth. And say we want to work out the velocity of this orbit. Well, we can work out the velocity of the orbit based on the information we know, or information we might have to know. So let's look at the equations that are involved here. Well, bear in mind, this is centripetal acceleration here. So it's going to be accelerated towards the center of the Earth at all points on this circular motion here. So we can say that we can bring up a previous equation with velocity in it, which is v squared over r is equal to g, which in this case is the centripetal acceleration, and this is the gravitational field strength at this point. Bear in mind, this is not g 9.81 g, this is just the g at this position here. Okay, it's likely to be a decent amount less than 9.81 by the time it's up in space. Well, yeah, as we are aware, that's a way of working out v. But in terms of what's going on in a kind of a field situation, we also know this equation to be equal to gm over r squared, because this is the equation for field strength in a radial gravitational field. And so what we've got here is we can actually set these as equal to each other. V squared over r is equal to gm over r squared. Now obviously, hopefully you can see that we can cancel these, and we can get v squared is equal to gm over r, and then that leads us to v is equal to square root gm over r. Now be very, very, very careful about this. Look at how similar this equation is to the one we've just derived. Now that's the reason I'm doing this in the same video. This is the escape velocity for a planet. It's got this ×2 factor in. This is the velocity for an orbit. Okay. Now the fun thing about this equation is that this is the velocity of an orbit at a set height from the planet. This is a really cool equation, because this is basically saying no matter what height, as long as you put it at this distance r, so here you go, distance r, then you are going to get this speed because you're around Earth. This is the planet, this is the mass of the planet here, so mass of planet that's creating the gravitational field in this case. Please bear in mind, this is the radius from the center of Earth. This is a very important point. It's often forgotten, or it's often posed as a little trick on the exam questions. You just have to be aware that r is the distance from the center of the Earth to where the satellite is orbiting in that case. Now, in lessons, we'll probably talk about the difference between the types of satellites. We'll talk about geostationary, and we'll talk about geosynchronous. Hopefully I spelled that right. Probably not. And we'll also talk about the one that's slightly different than those, which is why I'm going to do it in a different color, which is polar orbits. And your job before lesson is to hopefully go and look up how these are different to each other. They are specific. These ones have a similarity, but this is very different. And we want to talk about what the similarities and the differences are between these orbits before you get to lesson. Okay, so there's one more kind of idea we want to talk about here, which is orbital energy. Now, this is a really important point because we can talk about orbits in terms of their energy, and we want to talk about kind of working out what their energy is doing at any point in time on a orbit. So we could potentially look at a satellite as well. This is quite important. It's a nice, good point to start from. So if we have Earth here, and again we've got our satellite orbiting around. There's our satellite. Okay, that's our satellite orbiting around our planet. And what we're going to kind of look at here is the perspective of what is the energy that is, what's the energy considerations for something in orbit? Well, we've already talked a little bit over time about how, you know, at certain distances from the Earth, you could almost consider this to be like an equipotential line. Equipotential. Now, obviously, you'll remember equipotential lines are lines that indicate where the potential is constant at a specific distance from the center of the body that's creating that gravitational radial field. So it has constant potential on those any points. So it actually there's no work done in moving this from here to here, let's say, because they have the same potential in terms of the gravitational field. But let's think about this. Does this have kinetic energy? Well, hopefully you'll say yes, because it's moving. So because it's moving, it's got kinetic energy, which means it has a half mv squared. It's always a good old faithful equation, that one. It never changes. Kinetic energy is a half mv squared. But it also has a potential energy, which in terms of gravitational is gmm over r. And what you can do is you can say, okay, well, now remember this is negative. I always forget the negative sign. Don't forget the negative sign. Because what you need to be aware of for energy changes that occur, or energy in a satellite or some orbiting object, is that the total energy is made up of the sum of potential energy and kinetic. Now, I will draw your attention to something very, very important here. Look, this is a negative value, okay? So make sure that you treat this as a negative value. So if you're asked to do a sum of this, then this should be a negative value right here. So you'll have negative energy plus the kinetic energy. And so this is going to be a positive value. So think very carefully though, is this staying up in the air? Well, yes it is. It's not falling down, it's not changing potential. So actually its potential is going, you should, whenever asked for a total energy in a system like this, it should come out to be, sorry, not a positive, a negative value If it doesn't, go back, have a look, make sure you've not missed those negative signs for the potential there. But the point I suppose we want to make really is what happens when I change this orbit just slightly. Okay, so when I change this orbit just slightly. So in the real world, obviously, things don't orbit in perfect circles. They tend to be a bit eccentric. And you can actually call two different points on an orbit. This is a bit beyond spec, but that's okay. So if you have your orbit there, your orbit actually looks a bit like that. And what you need to consider actually is that this point here is actually given a name, and this point here is given a name because this is the closest point and this is the furthest point. And the furthest point is called the aphelion, the aphelion. So this is called the aphelion. And the closest point is called the perihelion. Now, what's interesting about this is that you can actually look at this from the point of view of, does the total energy change when the position of the orbit changes? Because obviously this is now closer and this is further. So you would maybe think that the total energy would change, but actually in an orbit, the total energy is actually constant. And we can prove that to you. Okay, so I'm just going to look up some data on my computer here, just so that we can talk about it. And do a nice little example. So, so say for example, we look at Mars around the sun. So this is the sun, and this is the aphelion, and this is the perihelion. So the aphelion is at a distance of 2.492 times 10 to the 8 kilometers. Just have to check my values. I'm just converting as I go here. And then the perihelion is at a distance of 2.066 times 10 to the 8 kilometers. And so those are the distances that are there, and also, so that's a distance, and we also have a velocity that I'm going to give you here as well. So a velocity is, for the aphelion, is 21.97 times 10 to the 3 meters per second. I've written that because I have it written here as kilometers per second, but that's what the value is. And the velocity here for the perihelion is 26.5 times 10 to the 3 meters per second. Okay, so bear in mind this is actual data about Mars. Okay, so this is Mars around the sun. And obviously I've drawn this quite eccentrically just to kind of show that it's actually an eccentric orbit, not perfectly circular. But you can notice there's only very slight difference in these values. So 2.49 and 2.06. I mean, I suppose actually in the grand scheme of things that is quite a lot. But you know, in astronomical terms, it's not that big. So let's look at some of the calculations we can do around this. And I'm going to do the perihelion here. And I'm going to do the aphelion here. And hopefully it'll all fit. It should all fit quite nicely. Okay, so with the perihelion, that's this one right here, we want to kind of work out and show that the total energy at this point is the same as at this point. So let's just look at some of the math that we can do to prove that. So GPE is equal to, and I'll write the equation up here because it's going to be the same for both. So GPE is equal to obviously negative GMM over r. And the kinetic energy is a half mv squared. Right, so GPE is gmm over r. So G, capital G, is 6.67 times 10 to the minus 11. And we've got the mass of the sun. So the mass of the sun is 1.99 times 10 to the 30, in case you didn't know. Sometimes that's a constant given in some data sheets. 1.99 times 10 to the 30. And then we're going to times that by the mass of Mars. And the mass of Mars, let me just check that real quick. So the mass of Mars is 0.642 times 10 to the 24. Nice and big. 0.642 times 10 to the 24. Obviously all divided by the distance, which the distance is for the perihelion, so it's this distance right here. Bear in mind this is in kilometers, so I'll pay close attention to that one. So 2.066 times 10 to the 8, but it's in kilometers, so I add an extra 3 because that's times 10 to the 3, so that takes me to times 10 to the 11 meters. And when I work that out, I get a value of negative 3.42 times 10 to the 32 joules. Okay, now we need to work out the kinetic energy. So kinetic energy is equal to a half the mass, so that's the mass of the planet, 0.642 times 10 to the 24. Times by the velocity, 26.5 times 10 to the 3 squared. And when I work that out, I get 1.54 times 10 to the 32. 1.54 times 10 to the 32. And that's joules as well. So here's the first example of seeing this in action. Hopefully I'm going to fit the amphibian calculations on the side. We'll have a good go at it anyway. So our final calculation is this one right here. So we've got the total energy is equal to the potential energy. So negative 3.42 times 10 to the 32. And we're going to plus the kinetic energy, 1.54 times 10 to the 22. And that's going to give us an overall value of negative 1.871 times 10 to the 32. Just push that up a little bit so you can see. Okay, so what I'm actually going to do is I'm actually going to leave the aphelion for now and actually let you guys follow this through. You've got all the data you need. You've got the mass of the Mars here. You've got the mass of the sun. You've got the distances up here. So this is this is a 2.492 up there, in case you were wondering. My bad handwriting. Watch out for the kilometers. 21.97 times 10 to the 3 meters per second for the velocity of the orbit at the aphelion. So see if you can show, and you should be able to see that you get the same answer with this one as I've done right here in the same way.